Hi, welcome back to ramanujan.math.circle, and today we're going to cover sequences and series. So let's start off by attacking basically what sequences are about, and we're going to start out with the very well-known and basic arithmetic progression. So what this basically means is that there's a series of numbers or sequence of numbers that's, you can write it out as A1, change the A1, A2, A3, so on and so forth, such that the difference between any two terms is D. And actually not the difference, but in fact, it should be a certain way of difference. So i.e. it should be A3 minus A2 is equal to D, and so is A2 minus A1, for example. And this is one of, like, whenever they say something is an arithmetic progression, you often use this you have this given property, and so you could use this to your advantage a lot of times. And so, like, obviously, if you rearrange this, like A3 minus A2 is equal to A2 minus A1, if you rearrange this, then you get that 2A2 is equal to A3 plus A1, and A1 plus A3 divided by 2 is equal to A2. And so basically the average of the first and the third term is equal to the term in the middle, which is the second term. So that's something you get out of there as well. So these are often very useful sort of properties. We'll look more into a little bit of properties in the next slide. But basically in definition, that's what it is. And D is basically called the common difference. That's the vocabulary you use of the arithmetic progression, or AP. Examples, for example, you can have negative numbers, of course, in an arithmetic progression. There's this example where it goes -7, 0, 7, 14. The common difference here is 7, as you add 7 each time to get the next terms. You could also have a negative common difference, and that's something you definitely want to look out for. For example, in this case, it goes 99, then 91, then 83, 75, so on. And here, the common difference is -8. You just have to subtract 8 each time to get the next term. However, we have something like 1, 2, 3, -4. This doesn't work because obviously the common difference here is 1, common difference here is 1, but then here it's -4 minus 3, so that's -7. So that doesn't work because these are not equal. So for example, this is not an arithmetic progression. Okay. So now let's look at some properties like I promised. So we're going to let an arithmetic progression for us be A1, A2, A3, so on until AN. AN is going to be the nth term, obviously. And arithmetic progressions go on, actually. So we have that the nth term, AN, is equal to the first term plus n minus 1 times d. And let me show you guys why this would be the case, just to enumerate that. And so we have that so this would be A, right? And then this would be A plus D. This would be A plus 2D, so on and so forth. So if you look at it, the first term has A plus 0D. The second term has A plus 1D. The third term has A plus 2D. So obviously this is term 1, term 2, term 3. So if you notice the pattern, we see that the nth term would actually be A plus n minus 1D, if you think about it. Because the first one starts out with adding 0 times the common difference. And so at the nth point, you would add n minus 1 times d to the first term. And so that's why that's why you have this. Okay, something about the common difference is that if you have the mth term and the nth term, am minus an divided by m minus n is equal to d. And that makes clear sense because am is equal to a plus m minus 1d, and an is equal to a plus n minus 1d. So if you subtract the two of them, so if you do am minus an, then this is equal to a plus m minus 1d minus a minus n minus 1d. And then these cancel, obviously, the minus 1d and the minus 1d. So then you're left out with md minus nd. And so if you divide that, obviously, by m minus n, then you get d, right? So that comes to show what that form or close thing form it is. If you have consecutive terms in an arithmetic progression, like I showed you before, if you had a n minus 1, a n, a n plus 1, then obviously you know that based on the fact that it's an arithmetic progression, you know that an plus 1 minus an is equal to an minus 1. So you rearrange this and you get 2an is equal to an plus 1 plus an minus 1, and then you divide both sides by 2. So an minus 1 plus n plus 1 divided by 2. And so yeah, that's how you get, it's equivalent to this. On a similar note, if there's some sort of term, if you have like a1, a n over 2, then a n. In fact, like, so if it's in between, if it's in the middle of the two of them, like that, so this is the first, sorry, the first term, last term, then we'd also have that n over 2 is equal to a1 plus an divided by 2. So this kind of like, you know, stretching it out, because say you have a sort of number line in some sense, your n over 2 is over here. So then you can go n over 2 plus 1, n over 2 minus 1. And that would follow this property in exact form. But then you could just extend that all the way to the end to n, and this one all the way to the end to 1, and it would follow the same property. Because you're adding and subtracting equal amounts. Here you're going to add, you're going to add some amount times d, and you're going to subtract the same amount times d here. So that's basically how you go about it. So to get the formula on that note, what you do is to find the sum of the first n terms of an arithmetic progression, you have that s is equal to n over 2 times a1 plus an. And if you write this out, obviously, you get this form, because you just replace an by a plus n minus 1d, or, you know, a1 plus n minus 1d. In that case, you get that s is equal to n over 2 times a1 plus a1 plus n minus 1d. This obviously becomes na1 plus n times n minus 1d over 2. That's what this is. And again, this follows from the fact that you can take, you basically pair up the terms on either end, and you keep averaging them, and they'd be the same average, and so you could just multiply that by n. So the proof of the AP sum, we could look into that a little bit right now. There's kind of two ways to go about it. So first, you can write the sequence in two different ways. You can write it in the forward way and the backward way. And what I mean by this is that you could start out with a1 and go all the way up to an, or you could start out with an and go down all the way to a1. And in this case, a common difference would be negative d, and this one positive d. So you're writing your sum as both ways, because obviously both terms will have the same number. So the sum obviously has to be the same. It's just ordered differently. And so now this is what you get. And you have s is equal to a1 plus a. So this is the normal sequence. They're normal going upward sequence. And this is the backwards one. Okay, so now you add the both of them. you get 2s is equal to a1 plus an. And every time you add these up, these cancel, the plus d and the minus d cancel, and these cancel, for example, and so on and so forth. So all you get is that you get n terms, 1, 2, so on, till n terms that are written as a1 plus an. And so this is obviously n times a1 plus an, and then you just divide by 2, so you get this. And then obviously, this is not exactly another proof, but in some sense, when you rewrite it, because an is, like I said, is equal to a1 plus n minus 1d. When you replace that in, then you get this. It's not really a second proof, but an expansion. So I'd encourage you guys to remember it this way, if possible. All right, so now let's go into an example. The terms of an arithmetic sequence add up to 715. So first of all, we're going to assume that there's n terms in this arithmetic sequence. And we're going to say they are, a plus d, a plus 2d, so on and so forth, until a plus n minus 1d, because they don't tell us how many terms. So we're told that the sum, so sum was NA over 2, or sorry, NA, my bad, NA plus n times n minus 1d over 2, and that's equal to 715. The first term of the sequence is increased by 1, so a plus 1. Second term increased by 3, so a plus d plus 3. Third term by 5, so on and so forth, until we have that the nth term is actually increased by, so it is n minus 1d times 2n minus 1. So because that's the kth positive integer, odd positive integer, and that's written as 2k minus 1. So that's our new sequence. So I'm going to call this S prime. So the terms in the new sequence add to 836. So we have, a plus 1 plus a plus d plus 3 plus so on and so forth, plus a plus n minus 1d plus 2n minus 1 is equal to 836. What I'm going to do now is I'm going to combine the terms from the first sequence. So a plus d, a plus 2d, so on and so forth, till a plus n minus 1d. Right, I'm going to combine this. And then I'm going to put the other odd numbers separately. So it's a1 plus 3 plus so on and so forth, plus 2n minus 1, and let that equal to 836. So now what we're going to do is we're going to substitute the value of s in here. So it's 715 plus 1 plus 3 plus 5, so on and so forth, plus 2n minus 1 is equal to 836. So now subtracting 715 on both sides, we got 1 plus 3 plus 5, so on and so forth, plus 2n minus 1 is equal to 121. So one thing I hope you all know, and if not, you guys learn a new thing, but the sum of the first k odd integers, meaning 1 plus 3 plus so on and so forth, so 2k minus 1, is actually equal to k squared. And so this property is very useful because now we can just replace this as n squared is equal to 121, and obviously the square root of that is 11. So we know that there's 11 terms. What are they asking for? They're asking for find the sum of the first, last, and middle terms of the original sequence. So obviously, one thing we know is that the sum of the first and the last terms, a1 plus an, is one thing. But then there's also the sum of the middle term, which, in fact, like we were talking about before, is actually a1 plus an divided by 2, because it's split in the middle of an arithmetic sequence, which is quite symmetric. So you can take the average of the first and last term and then divide it by 2. So now we're going to, sorry. So now this is just equivalent to 3 over 2 times a1 plus an, and that is equal to, so a1 plus an is equal to 2a plus n minus 1d. So 2a plus n minus 1d would be, well, so we have n is equal to, so we have that n is equal to 11. So one thing we can figure out from there is that, note that this is equal to n over 2 times 2a plus n minus 1d. And so since we have that n is equal to 11 here, what we do is we have that this, this expression is equal to 715 times 2 divided by n, and that gives us 65 times 2, which is 130. So then we have that this is equal to 3 over 2 times 130, and that's obviously 195. So that's our answer. It's a bit involved in terms of steps just to identify the things, but if you realize a certain, I think the main key turning point is like you can get all the way until this portion sometimes, but then after that, realizing this part, you know, that you can find this value actually is something that's a little bit more difficult to realize. And so what I would say is, once you've found a value, figure out by plugging things in what else you can figure out, or what other values you can find, because you never know. Oftentimes when there's a problem and you find some value, it can be very useful. We know, I think this would really follow for any math subject for that matter, like whether it's algebra, combinatorics, or geometry or things like that. But anytime you find something, figure out where you can apply this or plug in this number to get new values or new relations, because that can be really useful. All right, here's another example. I'll let you guys solve it and then we'll come back and discuss. So let me read out the question. Set A consists of m consecutive integers whose sum is 2m, and the set B consists of 2m consecutive integers whose sum is m. The absolute value of the difference between the greatest element of A and the greatest element of B is 99. Find m.